Hello. Welcome to Answer Everywhere. Today, we're continuing our look at designing chips, like you might design a GPU. This is a field that I don't know at all, and I'm trying to get a sense of how things like GPUs work, because they are going to run our lives. So last time, I took a look at some Verilog or VHDL implementations of GPUs. And this time I thought I would go one layer down in the chain to look at the code that takes the Verilog or VHDL source and starts to produce something that you can use for chips. So I asked all of the AIs about open source projects, kind of anywhere along the value chain here. And they all recommended Yosys for synthesis, which I think is kind of the analog in the hardware world of something like compilation, where you take the Verilog description and it converts it to gate level netlists, which are mapped to standard cells. I think this is the chat. So the bird's eye view is you do some essentially blackboarding, you design it, write it down, the designs on paper, and then you do some simulations and stuff. And then I think this is the level we were at, where the RTL, which is the register transfer level, which is the thing you code in Verilog or VHDL, you synthesize it into gate level netlists. And at this stage, according to ChatGPT, you do placement, routing, and timing optimization in order to meet the various requirements. So that's kind of what we're looking at. I don't yet know what exactly a netlist is. I think I looked it up, but we'll dig deeper into that. My camera is off today because I am sick. I'm going to have to keep pausing periodically to cough because I can't say more than a few words without going into a coughing fit. But when I post this, I'll edit that all out. I guess before we look into Yosys, let's take another look at netlist here. So according to Wikipedia, a netlist is a description of the connectivity of an electronic circuit. It consists of a list of the electronic components in a circuit and a list of nodes they are connected to. A network or net is a collection of two or more interconnected components. What I would like to do is be able to visualize a data structure or somehow visualize what a netlist is up to. So let's try an image search, because without that, I think I'm going to have a hard time of understanding what the requirements of the code are. Here is something. N is for netlist. I guess this is like an ABC book for your kids. This looks pretty good. It's way too zoomed in. This is maybe a visualization. A netlist is a list of nets that define the connectivity or interconnection scheme of your circuit board. They do not contain trace data. They contain information about how the points should be connected, not how the points are connected. For example, net A connects to net B will be written in a netlist, but something like net A runs parallel to the bottom left of the board for 3 inches, blah, 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 should not be expressed in that file. I guess that's the trace data. And I don't know, something like antenna, the physical layout is closely related, I would think, to the electronic properties. So I don't know how things like antennae are handled. But here we have what is possibly a netlist. This is maybe defining a net. LED2 active is probably a name. And some things are joined. I'm guessing these are all joined together. And then this is a port ref, maybe with this human readable name, possibly, and this like unique reference number or something along those lines. For your designs in college, you may not need to review or edit a netlist file. But as designs are more complex, you may need to go back, etc. Okay, thanks, Shivani Joshi. Okay, so that's possibly what a netlist is about. Let's figure out what Yosys does. I don't think they have a Wikipedia entry. We have a comparison of EDA software. Yeah, so it should be logic synthesis. So I'm thinking it should somehow connect up, it should connect things to gates ultimately. Logic synthesis is a process, by which an abstract specification of desired circuit behavior, typically at register transfer level, is turned into an implementation in terms of logic gates. So we should get the classic logic gates, and these should have like a standard or at least decipherable physical implementation. And we've got Charles Sanders Peirce showing up here. So we know we're close to the math. All right, now let's look at Yosys. And then the other one I have open, I don't need Emacs right now. The other one I have open is OpenROAD, which should be more about layout. OpenROAD, which stands for Open Rapid Object Application Development, is a 4th generation programming language and development suite from Actian Corporation. Actian sounds like they sell medications. It's related to the Ingress relational database, which I think Postgres is post-ingress. Is that right? But also, this is written like an advertisement. No, Ingress is a proprietary database. Okay, so maybe it's just Gress that is pre-Postgres. But let's take a look at OpenROAD in the background. All right, and we'll start with Yosys, and then we'll look at OpenROAD, and we're really just going to scratch the surface because I want to see what these things are about more than anything. I'm not going to understand really the implementation details at all, not in a first pass. We have a README, stuff about building from source. I don't think I'm ready for that level of commitment. We have code owners, and we have C++, Verilog, Python, Yak, and System Verilog. And passes may be related to like compiler type passes, libs. Kernel is probably important. Guidelines might be important. Front ends might be important. Back ends is probably important. This kind of looks like it's laid out like a compiler repo with front ends, back ends, and passes. Here's examples. I don't know what these are. Alger, CMOS. CMOS I think is relatively simple. Intel. Let's look at Intel and CMOS. And DE2I 150 and Max 10. I don't know what DE2I 150 is. It's an FPGA thing, development kit. And it looks like that. All right, and so what do these files look like? We have this Quartus compile, we have some Verilog. 7seg is probably like a 7-segment display. Like the thing that displays integers and numbers in the old time days. Like this. Like ye old digital clock. Draw ye old digital clock. All right, so here's the digital clock. I want it to make it look old timey, like a relic of the past. Great. All right, so we have this 7-segment display. We've got these 4' H1, 4' H6, etc. We've got what's obviously, so this is Verilog. We've seen the Verilog syntax yesterday. Not yesterday, but last week. These are just defining some stuff. I'm assuming this 7 might mean 7 bits. And I think Quartus compile is probably what I want. Runme Quartus might just be a bash script. Export, yeah, some bash script. So what is the QSF and QPF files? This seems to be something very procedural. It looks like maybe we're going to execute one line at a time. This is creating global assignments. Like the name family is probably being set to Cyclone IVGX and the device and so on. Here's some DRAM stuff. And we've got the same name being reset. So I guess the name is not like a unique identifier, whatever this is. But or I guess DRAM adder is maybe one of the gates. I don't know. But set instance assignment is different from global assignment. And we have other set instance assignments like the clock 250, clock 350. We have LVTTL. I don't know what those things are yet. But we've got a bunch of DRAM stuff. And then whatever this BA, I don't know. CLK is probably clock. And then we have DRAM DQs. I don't know what those are. And I'm guessing that these things on the right after the 2 are possibly gates. These are maybe Lego bricks that you can use in Yosys to build up your designs. And this QPF file just has nothing of interest. Basically metadata. Here's CMOS. We've got some Verilog, whatever a .lib file is. This might be Verilog. And then do we have Q files? We have an SP file that has things like simple transistor model CMOS N, and NOS level 1, blah, 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 blah. Load design and library. I don't know what format this is. Maybe that's system Verilog. Maybe let's just ask one of the AIs. What programming language is this? And let's ask 2.0 Flash. It's the SPICE simulation program with integrated circuit emphasis. Okay, so it's probably some simulation program. That makes sense that it's called test bench. And then where is maybe YS is the Yosys stuff. Read Verilog counter V. You're going to, I guess, read that Verilog file. Read a lib file. We'll call synth, which is maybe just going to synthesize. And then we have diff libmap. Liberty is maybe telling it that it has some freedom as opposed to like being over constrained. And so on. I'm not sure. Use synth command. Okay, so we've seen some examples. I don't know what to make of them. Okay, so now that we've seen some examples, maybe we can dig into the code a little bit. So we have passes, and it has things like equiv commands, FSM, hierarchy, memory, opt, pmgen, proc, sat, tech map, and tests. Shall we look at commands? Auto name, presumably it's going to come up with an automatic name. Delete, cover, copy. These are C or probably C++, because they have the CC syntax. Is synth one of these files? I don't know. But somehow we've got commands. Let's look at what a command looks like in general. We've got static void unset drivers. You're going to pass it in some sort of design, RT-lil design, an RT-lil module, in a sig map, probably something like a signal map, and a sig spec. And then we've got cell types. We're going to do some dummy wiring. And I guess we're going to iterate over the cells, at least to call them all once. Then we're going to iterate over the connections. That gives us a port. And we're going to check if the cell output, given the cell type, is the port's first thingy. Then we're going to call sigmap and pass in the port second and replace it with like the dummy wire, I guess, or something along those lines. So we're doing something with wiring up. And then we've got this connect pass. The connect pass is a struct, so basically an object. It's got a help function. So you have some sort of user interface, I guess, where you can ask for help for all of the commands. And you've got execute. So presumably this is, it extends this pass thing. So the pass class or maybe abstract class has some sort of interface that includes help and execute, I assume, since this is override. And so is help. And we're going to iterate over some stuff. There are arguments that are passed in. You pass in the design as a whole. And then this is just argument parsing. And we're creating a sig map and iterating over some connections, kind of depending again on what the arguments are. Okay, so this is just C++. So that's a pass. Here are libs. These must be the dependencies. Kernel has a bunch of stuff like cost. Let's look at the cost header. Should we look at, I guess we can look at driver CC, FF merge. We'll just open a bunch of these. We have a JSON, some sort of JSON implementation. Mem.h, mem.cc. I guess I'll look at those. These RT-lil seems like it's got some of the fundamental types. Satgen. This is S expressions, I assume. And then we have Yosys. This might be the entry points. And then common. And then Yahweh. And timing info. We'll just open a bunch of those. Those are going to be after whatever I had opened previously. Guidelines just has this, like, this is like human readable documentation. And then front ends. We have Verilog, RPC. Is this like for communicating over RPC, or is this like a different hardware description thing? I don't know. Yeah, some RPC server. Whatever Bliff is, JSON, Eiger. Whatever Eiger is, it's a thing that you might be able to possibly convert to and from Verilog. AST is probably just the abstract syntax tree. And then Liberty. I thought Liberty was maybe saying that it has Liberty with some satisfiability thing, but maybe Liberty is another product. How about FPGA? Yeah. Some open source Liberty format. I don't know. Something to do with chips and whatnot. And then we have, for backends, we have more stuff like more Eiger, InterSynth, functional, simple C, SMV, Spice, again, Verilog. So I'm guessing that, I don't know. Some of these are probably mainly used for describing the netlists. And some of them, like Verilog, it might just be translating. It might just be have the ability to translate from one kind of RTL language to another. What is RLTIL? Is that what it is? RTL. It's RTLil. Okay, so RTLil is an intermediate language. Great. All frontends, passes, and backends in Yosys operate on a design in RTLil representation. The only exception are the high-level frontends that use AST representation as an intermediate step before generating RTLil data. Okay, so we've seen the RTLil design. The design, I guess, has modules and cells and wires and memory and whatnot. Okay. Then we have tech libs like GateMate, ICE40, Intel. Let's look at Intel. Synth Intel. This command run synthesis for Intel FPGAs. Okay, so this is maybe it's aware of Intel FPGAs as like a target, I guess, and it's trying to synthesize things for Intel specifically. And this is maybe something like a gate, something like a Lego. I don't know. Tests will ignore cost.h. I assume this is some sort of cost calculation. Cell costs. You give it a design, and we've got some default gate cost. Default size heuristics for several common PDK standard cells used by ABC and STAT. So for example, I guess this probably means a NOR gate has cost 4. A buff gate has cost 1. And a NOT gate has cost 2. What is a buff gate? It must be like a single thing. If we were to connect two inverter gates together so that the output of one fed into the output of another, the two inversion functions would cancel each other so that there would be no inversion from input to output. While this may seem like a pointless thing to do, maybe that's what we saw with the two tildes. It does have practical application. Remember that gate circuits are signal amplifiers, regardless of what logic function they may perform. Is this just for this purpose, a special logic gate called buffer is manufactured to perform the same function as two inverters. Its symbol is simply a triangle with no inverting bubble on the terminal. Okay, so it seems like it's basically an amplifier. Why is it called a buffer as opposed to an amplifier? I don't know. And presumably we're going to somehow take the costs and when we lay out some stuff, we're going to try to minimize cost relative to all the layouts that otherwise work or something along those lines. Here's driver. I don't know what driver will do. We've got a main function. Whatever EM assembly is, we're going to make a directory called work. So I guess this is just driving the program. And then we've got a run function. So it's making a work directory, doing something with Python. We're going to get the size of the design. And we're going to call run pass on the command. And somewhere there's probably a loop that gets all the commands. Here, this main thing is probably that loop. And we're going to parse options and everything. Okay, so that's like the entry point. FF merge. I don't know. A helper class. What is FF? Let's look up Yosys FF. It's probably not feed forward. Let's ask the AIs. And Yosys, what does FF mean? Flip. Oh, it's a flip-flop. Okay. So it's a flip-flop. It goes flippity-floppity. This is about merging flip-flops. I guess it's clear why you would need that. FMT, I don't know what it is. Maybe format. Maybe we're just formatting Verilog. We're just going to plow along. Here's memrood. 1 bit for every write port. True if and only if simultaneous read and write port, blah, blah, blah. We have memwrite, mem, and so on. I'm going to plow through so I can make sure that I look at the OpenROAD thing. Here's some RLTL stuff. We've got a state, which is some enum, and a sync type, like I guess whether it's edge sensitive on the positive edge, the negative edge, or both edges, etc. And some stuff about checkpoints. And I don't know. We're popping and doing stuff. So it seems like we've got some sort of queue. I'm going to ignore this. SatGen, I guess I don't really care what it is. I want to just kind of plow along. We've seen an entry point, so I don't need to look at Yosys. But I do want to see, there's like DRAM stuff, and I want to see where that stuff is. DRAM adder. I don't know if that's just a string that makes sense to the Intel FPGA. Okay, so DRAM adder only is in this file. So I'm guessing that it might be part of the Intel thing. And I want literally the string. Yeah, it seems to be maybe about a specific device. Okay. So we saw a little bit there. We saw, we were beginning to see like it playing around with gates and merging them and assessing their costs and everything. And somehow that's going to produce a net list, I assume. And now we'll look at OpenROAD for just a few minutes. Foundations and realization of open, accessible design. No human in loop design with a 24-hour turnaround. Okay, so you can build it. How about a tutorial? I don't need Git. It's hard to find out what it is actually supposed to be doing. But we'll look at the code anyway. All right, let's see. We have Docker. I guess you can run it in Docker. We've got some Etsy stuff. Source. So we have ants, which is good to see. DFT. Inscrutable names. DST. I don't know. GUI. I guess they couldn't afford more than 3 letters per directory. We have design.i. That might be interesting. We have main. I'm going to ignore main. We have this Python thing. It can be run using Tickle and Python with limited support. So I have no idea what any of this is going to do. Okay, so whatever DFT is, we have architect cells, clock domain, config, replace, stitch. Should we look at architect? Scan architect, scan chain. And this is C++. Contains all the scan cells of the design and maintains them separated based on the hash domain. Scan cells bucket. We've got some scan cells bucket. We've got some number of cells. Some hash domain lists. I don't know what any of that is. DPL has things like coordinates. This is, I guess, now we're in like layout space conceptually. Graphics. Grid. Let's look at grid. I don't know if this is for the GUI or for the chip. We've got a grid interval with a low and a high. It's like the X, what's the word? Like granularity or something. And we've got a pixel, which has a cell, a group, whether it's valid, and so on. Yeah, I don't know if this is for the GUI, again, as I said before, or part of the layout. Here's objects. Get edge type, get bounding box. I'll just ignore this. DPO. We've got opt DP, color, architecture, detailed. Detailed displacement, detailed generator, detailed global. Okay. DRT. And again, inscrutable names. Graphics factory. Triton, I think, is a GPU thing. So I don't know what that is. So DST, balancer connection, distributed. Worker. So we're doing something maybe in a distributed way with workers. Constructor for accepting connections from client. So maybe this is just because we're doing hard work and we need to parallelize it. Here's, I guess GUI does have its own directory, which we will ignore. GPL, what is that for? We have fast Fourier transform, I think. FFT, it's got a bin count X, bin count Y, bin size. And then something about bin density, electrophi, electroforce. So it looks like now we're doing possibly physicsy stuff. And so on. Cut, no, not cut. CD, FD, FT, 2D. And I guess these are maybe just FFTs. GRT, who knows? We have things like a global router, a grid, a grout renderer, make wire parasitic. Yes, let's look at that one. So we've got some wire, we've got a logger and a resizer and a db sta and a db tech and a db block and some router. And we're going to estimate parasitics and so on. I don't know what parasitic means in this context. In general, parasitics, what? Please load. They occur when you have multiple conductors in close proximity. So this is parasitics seem to be about electronics that don't satisfy their like ideal properties because they're too close together in some sense. And we've got layer RC get cut layer res dBu to meters, etc. Okay, this seems to be doing stuff with wires. So this, I believe that this is now at least trying to figure out whatever GERT is. GERT seems to be trying to figure out something about the chip itself as opposed to graphics. We've got net, which I'm going to guess is about the like netlist type of thing. Whatever slack 0 is, maybe it doesn't have any slack. It may have wires. It may be a merge net. And we're going to get const name and so on. We can add a pin. We're just going to fly on through this thing just to get a sense. Okay, here's floor plan. This is the sort of thing I was hoping to see, I think. What is this? Is this tickle? It's a .i file. We've got a lot of percent signs. So we've got init floor plan core. Give it a design, a die that has maybe length, X and Y, and whatever U is, X and Y. And then the core also has LX, LY, UX, UY. And then whatever a site is, but there may be additional sites. And something about row parity. And you've got a set of flipped sites. And then the design has a floor plan function. It has a floor plan which you can get, and then you can init the floor plan, passing in all of this stuff. And here's that function. No, this is not that function. This is just another util that calls the same thing. You can insert tie cells. And we're just getting the floor plan. So now what I want to do is I want to see where get floor plan is defined. Because that will take us closer to where we want to be. Okay, design.h, ord. Of course, it's in the ord folder. Okay, so what does the design have? We can read db, write db, write def. I don't know what db we're reading or writing to. We can read Verilog. We've got this link thing with a design name. You can check whether something is sequential, whether it's a buffer, whether it's an inverter, whether it's in the clock. We have an antenna checker, some Triton stuff, and these are services. Okay, so one service, I guess, will do antenna checking. I presume one service will do replacing and finales and restructuring and resizing. And that's the basics of a design. Let's see what else is in the ORD folder. OpenROAD header. So let's maybe look at these class macro placer finale. Let's look at antenna checker. Oh, we're just declaring it. Do we have a write DB? No. Oh, this is just the header anyway. What about tech? Oh, we're in the include directory. Is there an ORD that's not include? No. Let's try just searching for floor plan. This is include. Maybe IFP is a knit floor plan. I don't know. Source IFP source. Okay. Do you have an implementation? All right. So where does utilization come from? Doesn't seem to be an argument. We've got some validator. These seem to be just checks from the validator. We're going to take utilization, divide it by 100. And get the design area, divide the design layer by utilization, take the square root, and that's the width. We'll round the core width. We'll take the core width, multiply by the aspect ratio. That's in general going to give us some irrational number, or technically a rational number, approximating some irrational number. And we'll round that, I guess, to an integer. And then we'll call init floor plan. And where is this function defined? In this file. So here, we're going to give it a die and a core and a base site. And we're going to call it die area. And we'll snap to MFG, I'm going to guess is manufacturer grid. So we have some, the die has some dimensions, I guess, and the manufacturer has some grid that you have to work with. So you'll snap to the grid, and then we're going to call set die area. And if we're not a base site, we're going to return. Then we are going to get, I guess, all the sites and their names, check if they have a row pattern. And if they do, we'll get, I guess, the sites in the row, presumably, is what they're doing. Then we'll get the additional sites and we'll add everything to the used sites and remove all the rows, etc. So this is just initializing, but it's at least telling us a little bit about what the objects are, what the conceptual domain looks like. Here's a init floor plan update voltage domain. This function is used to create regions, split overlapped rows, and create new ones. Okay. So something about voltage domains, I don't know what that is. You can make tracks. This is calling some make tracks function. Maybe this one. You've got more validators. Something about offsets and pitches, I don't really know. We're going to take whatever block underscore is. We're going to find the track grid, passing in the layer, and doing some other stuff. And then we can also make tracks non-uniform. So that's initializing the floor plan. What else can we do? Also, what is is IFP just initialized floor plan? Are there any other FP things? Is there anything called optimize? So we have a couple of things here. One, something called a delay optimization strategy. We also have a logic optimization strategy, a zero slack strategy. So these seem to be different strategies. I don't know what the RMP directory is. Let's open RMP. Maybe there's a README. There is. Okay. Restructure. The restructure module in OpenROAD map is based on an interface to ABC for local resynthesis. The package allows logic restructuring that targets area or timing. It extracts a cloud of logic using the OpenSTA timing engine and passes it to ABC through BLIF interface. Okay. I don't know what ABC is. I don't know what BLIF is. Let's find those things out. Do we have an ABC directory? No. We have an ABC library. That's in the RMP directory. So ABC is a growing software system for synthesis and verification of binary sequential logic circuits appearing in synchronous hardware designs. ABC combines scalable logic optimization based on AND inverter gates, AIGs. That's maybe related to Eiger, the Eiger we saw in the Yosys repo. Optimal delay DAG-based technology mapping for lookup tables in standard cells. Provides an experimental implementation of these algorithms and programming environment for building similar applications. Okay, and this seems like a good thing. I will read it. So I don't really know what this means. So we're going to synthesize, which is what Yosys did. So maybe that means synthesize from RTL. And then we're also going to verify. What are we going to synthesize? Verify binary sequential logic circuits. Binary, assuming they mean it works in binary like an ordinary digital computer. Sequential logic circuits. Maybe binary means something else. I actually, now that I think about it, it probably does mean something else. Sequential, I am assuming they execute in sequence, and logic meaning they execute logic. Appearing in synchronous hardware designs, I guess, as opposed to async designs. And it has scalable logic optimization. Scalable maybe meaning you can do things like parallelize it based on AND inverter graphs. So building up some sort of graph, I guess, based on the circuits. And then once you have those graphs, I guess you can do nice optimizations and stuff on them. Optimal delay DAG-based technology. I don't know what optimal delay is. Maybe just making sure things are fast based on building a directed acyclic graph. Mapping for lookup tables and standard cells and innovative algorithms for sequential synthesis and verification. Okay. I'm mildly curious what, I want to know what this is. Binary sequential logic circuit. Mainly I want to know what binary means. Well, that's Gemini. What is a binary sequential logic circuit? It remembers its past, unlike combinational circuits, where the output depends solely on the current inputs. Sequential circuits remember previous inputs and outputs. Okay, so I was totally wrong on what sequential means. This memory is crucial to their functionality. Uses binary signals. All signals within the circuit are represented by two discrete values, 0 or 1. Okay, so I was right about what binary worked, which is I was much less sure about. It incorporates memory elements. These circuits utilize memory elements like flip-flops to store information about previous states. Key characteristics. The current condition of the circuit, determined by the values, blah, blah, blah. Yeah, okay, I understood that part. Okay. Write 5 tweets decrying how terrible binary sequential logic circuits are and how the people who like them are bad. That's not a tweet. An image is not a tweet, Gemini. Okay. Binary sequential logic circuits are so last century. I'm not sure what's worse, binary sequential logic circuits or the people who insist on using them. Okay, these are not bad. I'm so tired of binary sequential logic circuits. They're slow and efficient and they make my head spin. You're probably a fan of dial-up internet and payphones, just saying. Okay, well, there we go. All right, so it's using ABC for kind of the layout stuff, I guess, whatever this module is. I don't know how important this module is. The code is kind of unreadable because of all the names. But I'm kind of getting a sense that it's laid out in these modules. These modules probably have representations in the documentation. And I will look up OpenROAD modules. What if I just look up OpenROAD RMP? Is that likely to take me to documentation where I can click around? Restructure. Okay. Yeah. Nope, I can't do that. So it's mimicking the source tree. In fact, this might just be the source. But it's maybe only rendering the documentation stuff. Okay, so this is literally just the README in the documentation. Okay, I don't know what a tap cell is. A command that inserts tap cells or end caps. Well tap cells in physical design. Well tap cells are used to prevent latch-up issues in the CMOS design. Well tap cells connect the end well to VDD. Yeah, I don't know what that means, but you probably might know what that means if you know hardware. We also have pin placement, I'm guessing for like when you have like physical pins sticking out of your board that are connected to wires. Restructure, partition management, whatever PDN is. And every time I click on something, this scrolls back to the top, so I can't click on the next thing. So global placement, GPL, is based on the open source replace tool from the paper, Advancing Solution Quality. All right, and I got to drop off just about here. So this is kind of, it seems like it's using other tools to do the actual hard work. So that's cool. And this particular tool does the placement. It's doing something. You know what? I was ignoring the ant directory because I thought it might be the ant build tool. Maybe it's ant swarms. At any rate, there's some paper, and it's an analytic and nonlinear placement algorithm. Solves electrostatic force equations using Nesterov's method. So Nesterov is doing some force stuff. It's figuring some stuff out. Maybe this is just a candidate layout and it's finding the forces or whatever for one, and then based on that, it's going to do something else. Let's look in the ant directory just to see if there's anything interesting there. And ant is antenna. Okay. We've got polygons. So you have antenna, and then what about something like genetic? I don't know how it does optimizations. Maybe the optimizations are all done by modules. What about something like just the word algorithm? We have the Hungarian algorithm from Monkrace. Monkrace wrote an influential undergraduate topology book, but I assume it's not the same Monkrace. The Hungarian algorithm. It sounds like it might be well known. Is a combinatorial optimization algorithm that solves the assignment problem in polynomial time, which anticipated later primal dual methods. Okay, so we've got some cool stuff. I don't know what monk race is. I kind of want to see what that's about. The Kuhn monk race algorithm. Didn't I already? Okay, so James monk race. I guess it is the same monk race. Well, there you go. So I got to hop off. Thanks for joining me. Bye-bye.